when you're dealing with arithmetic sequences, where every term is separated by the same amount, these are the two equations you want to memorize. Okay? This is the explicit definition for the nth term, and this is the sum of the first n terms. You with me?
Yep.
Okay, in this problem 17, it basically produces a sequence, an arithmetic sequence. We have 2, 3, 4, 5, 6. What's the number of pipes in the 19th layer?
In the 19th layer would...
Here's the way you want to figure it out. What's the number of pipes in the top layer, the first layer?
2.
Second layer? Second layer?
3.
Third layer?
4.
19th layer?
19.
No, every one was one more. In other words, the first layer was 2 pipes. Second layer was 3 pipes. Therefore, the 19th layer is 20 pipes. You see why?
Yep.
In other words, the first layer is not 1 pipe. It's 2. So the 19th layer is not going to be 19, but 20. Now, our goal is to figure out the sum of that. So, S sub what? Is it S sub 20 or S sub 19?
S sub 20.
Actually, it's 19. In other
boy.
words, this number refers to which term of the sequence we're talking about. Okay, well, n is 1 there, it's 2 there, it's 3 there. By the time we get up to there, it's going to be 19. So we have 19 terms in our sequence. So we want to sum the first 19 terms of that sequence. Well, n is 19. First term is 2. Last term is 20. Divide by 2, and we're going to have our answer. 19 times 11.
201. No, 209.
208, I think. Let's see. 10 times that is 190. And if I add one more 19 to that, it's 209. That should be the answer. Okay. Now, let me give you a little clue here. I'm assuming that when you take a test, they don't give you any of these formulas, right? They expect you to memorize them?
I actually think they're giving us on this test.
Okay. If you have any question, in other words, if you do have to memorize it and you're not sure you got it right, take a simple sequence like 2, 3, 4 and figure out what the sum is. We can tell the sum is 9, but in our case, that would be the sum of the first 3 terms, which would be 3 times 2 plus 4 all over 2. 3 times 3 is 9. In other words, by doing a small sequence of small numbers, we can verify that we memorized it properly. And you can do that with both of these formulas. In other words, if you're not quite sure you've memorized either one of them, you can always do what I just did by taking a really small sequence. In other words, I don't want to have to add 2 plus 3 plus 4 all the way up to 20. That's laborious, especially they might have said, what's the 200th pile, you know. And then you'd have to do it this method here. You wouldn't be able to count it out. All right, 18. I love these kind of questions. You're the only student I get that has these kind of questions. Nobody at Chatfield studying arithmetic sequences is going to give me questions like this. So let's look at 18. Find all the positive integers less than 500 that are divisible by 11. Well, if I start drawing that sequence, that's our sequence, right?
Yeah.
Out to what? What's the last number? Do you have a calculator? Or do you have your calculator?
Let me use my phone.
It's 500 divided by 11.
45.45 repeating.
Okay, so the last term is going to be the 45th term. And what is that? 11 times 45 is
405.
10 times 45 is 450 plus another 45, 495. Is that what you said?
Yeah.
So that's our last number in this sequence. Okay, and that's how I figured it out. Maybe there's a better way to do it. I don't know. Now, we have to answer one more question. How many numbers are there in our sequence? Because I can't solve for s sub n until I know what n is. In other words, is n the 45th term? Or is n perhaps the 46th term?
45th.
You sure? Would you bet your life on it?
What?
Would you bet your life on it?
No.
Right. You'd want to prove it, right? Look at these first three terms. How do I get how many terms are in that?
3.
Well, I take 33 minus 11, which is 22. I divide it by 11, which is 2, and then I always have to add 1. Understand what I just did there?
Yeah.
Okay, well, let's do the same thing with our sequence. So I'm going to take the beginning of the sequence is 11, the last number is 495, so I'm going to take 495 minus 11, which gives you 484. I'm going to divide it by 11, which gives you 44, and I'm going to add 1, which gives you 45. So you were right, and I thought you were, but I know it's really easy to get off by 1 in some of these. In other words, to figure out how many terms were in this, I had to take that minus that, divide by 11, and then add 1 to it. So being off by 1 is a very, very common problem whenever you're dealing with rows and stuff. Do you ever use a spreadsheet
Yeah, rarely.
Well, sometimes they'll say on a spreadsheet, how many rows do you have between row 8 and row 412? How many rows do you have between those two? In other words, if you got a big spreadsheet and you're on row 8 and it goes down to row 412, how many total rows is that?
402.
Well, if you subtract the two numbers, you get 404, but you always have to add 1. How many rows are there, and the reason why? How many rows are there between row 8 and row 9? 2, right? If I just have 2 rows, there's 2 rows there, so I know there's 2 rows, but if I just subtract 9 minus 8, I get 1. So you always have to add 1 when you're talking rows and numbers and stuff. And that's why I added 1 when I did this calculation. Technically,
Rows between 8 and 9.
there's 2. If I have not between 8 and 9, counting 8 and 9. In other words, if I count 8, let's say how many rows are there between 8 and 10? Counting 8 and counting 10, well, there's 3 rows, right? That's 1, 2, 3. But if I just subtract 10 minus 8, I get 2. So you always have to add 1.
Okay.
Unless you're talking about the number of numbers that are between 8 and 9, and then you subtract 1. In other words, there's always that 1 that kind of has to be dealt with. The way I really figured out how many terms there were was I subtracted 495 minus 11, divided that by 11, and then added 1.
Okay.
And that's how I got 45. So how do I figure out how many numbers there are? How many multiples of 7? Well, we got our answer, 45. It didn't say sum them all up. It's how many terms are there in this sequence. So that's 18. 19, kind of similar. What's the first multiple of 7 after 99? Divide 7 into 99.
Would be 105.
Hold on, you get 14 with a 1 remainder, right? Which means 7 times 14 is 98. So our sequence doesn't begin at 98, it begins 7 after 98. So the first term of our sequence is 105. You figure how I got that?
Yeah.
Okay. The next term, multiples of 7, well, I'm just counting up by 7s. Each of those is the next multiple of 7. What's the last one before 999?
It would be...
Divide it into 999. And you get 1, 4, 2. So, and now if I multiply 7 times 142, I get 994, right? And the next higher multiple is 1001. So this has got to be my first term, this has got to be my last term. How many terms are in that sequence? How do you do it?
Here, it would be...
Just tell me how to do it and I'll write it.
I did 105 divided by 7, so I got 15, and then I did 994 divided by
7.
7.
And you got 145.
Yeah.
So that's not a bad way to do it, but you're still going to have to add that 1. Here's a better way that I like, is I'm going to take the last term, subtract the first term. What's that? 889. Divide that by 7 and add 1. That's how many terms there are in that series. In other words, you take your last term minus, that's kind of what you did. You divided your last term first by 7 and your first term first by 7, and you took that answer, but you're still going to have to add 1 doing it that way. What's that?
Oh, so yeah.
Okay. But this way is a little clearer. The reason it is because this method is relatively easy to prove. If you're taking a test and you can't figure out whether you got to add 1 or not, do it with 2 or 3 of these numbers. In other words, take these first 3, do 119 minus 105 gives you 14. Divide that by 7 and you get 2, and I can plainly see there's 3, so I'm always going to have to add 1 to that. Okay?
Okay.
All right. A woman begins working for $30,000 per year, gets a $2,000 raise each year. Give me the sequence that we're looking at. What's the first term of the sequence going to be?
The first term is going to be 3,000.
30,000, right?
30,000.
What's the second term going to be?
32,000.
Okay, I like to write, hold on a second. One thing you don't want to do here is use commas for distinguishing a number like 30,000, because it's going to get in the way of the commas that separate the terms. So I'm going to write 30,000 like that, 32,000 like that. Can't help myself. I'm so used to putting commas there. But you can see the problem if you do put commas is it becomes really confusing to read. So some number I'll call x. If I can figure out what x is such that the total of all of these is greater than 1 million. Let me think for a minute. So I'm saying S sub n has to be greater than 1 million, and S sub n is equal to the number of terms times the first term plus the last term, which we don't know, divided by 2. Well, let's think about this for a minute. That's all true. It just doesn't help me. I can't solve that. So let's go about this slightly different way. Let me think for a moment if I can even jerry-rig this. In other words, just by trial and error. Let's see. What if my sequence is this? And then I know that I'm going to have 30,000 times whatever that is. Well, when you're faced with a problem like this, I'm sure that I'm missing a particular method of solving it, but I can come close by approximating what x might be. In other words, let's see. If she worked there for 20 years, then she's going to have 20 times 2,000. So her salary on the 20th year is going to be 40,000 more than the start. So let's say her salary on that last year is 70,000. Now, what is let's see, and that's the 20th term. So let's see what S sub 20 is. I hate doing problems like this, but it'll let us know whether or not we're even close, and we'll be able to adjust accordingly. That looks awfully close. 30,000 plus 70,000 is 100,000, divided by 2 is 50,000, times 20 is 1 million. Wow, what a good guess I made. So there are 20 years, exactly. Hold on a minute, let's see. This is, I might be off by one. That's the first year. That's the second year. So the second year, let's see, if I multiply 2,000 by 1 and add it to 1, okay, I'm multiplying 2,000 by 20, adding it to 1, that's got to be the 21st term. Because, yeah, in other words, again, the third term would be 34,000 minus 30,000 divided by 2,000 plus 1. That would be the third term. 34,000 would be the third term. So 70,000 minus 30,000 is 40,000. Divide by the common difference, which is 2,000. You get 20. Add 1, you get 21. So the sum of 21 numbers would be over a million. So what is the sum of 20 numbers? It's exactly 1 million. The first 20 numbers in that sequence total a million based on that formula. And that means that 20 years is the answer. But her salary on the 20th year is not 70,000. It's 68,000. Not that they asked, but we can see that it is. In other words, as long as I know that the sum of 20 terms equals 1 million exactly, then I know it's 20 years. There's probably a better way to do this problem than the way I did it, because what I did was I guessed 20 and then checked and see, well, how much would you make in 20 years with this sequence? You make exactly $1 million, which is what they asked. That's the answer. Now, I was pretty lucky with my guess, but I didn't totally guess. I knew that I was getting 2,000 raise per year. I'm not sure how I made such a perfect guess the first time. It's a little bit intuitive almost. But anyway, let's go on. Well, we've run out of time, unfortunately, before we could do many of these. I noticed that 25 through 28, or rather 23 through 26, are going to be geometric series. In other words, whenever you see it rises 9/10 as far as it did in the preceding 30 seconds, you know that every term is 9/10 of the previous term. And that defines a geometric sequence. So the very first thing you have to ask yourself on any of these problems is, are we talking an arithmetic sequence or a geometric sequence? Once you figure that out, then you're going to use these two equations. I didn't have to use the first equation at all. Maybe I needed to for that last problem. I don't know. These are always a little tough. They're impossible if you don't know these formulas. Even knowing these formulas, they're a little tough. And as you can see, it's really easy to be off by 1. Okay? Next time, I'm going to remember that you don't have your phone, because every single time I send the meeting ID number to your phone, and then I get a text about 3 minutes later from your mother saying, can you send it to me? So I'm going to, for the time being, I'm just going to make your name her number, and that way I won't have any problem.
Okay.
Okay? And then if you get your phone back or get your phone number back, always let me know, and I'll change it. But for now, I'll just take that number that I texted it to her and make it your name.
All right, sounds good.
All right, Jake. Have a good week. I'll talk to you next week. And we're doing Tuesdays now, right? At 5:30 every week?
Yeah, I believe so.
Yeah, I had a little bit of a problem. I had you listed on Monday and Tuesday this week, and I was going to call you, and then I got an email from your mom saying, no, the Monday one wasn't right, but the Tuesday one was. So. All right. If you see that you got a lot of problems like this, you may want to add a half hour to the tutoring or something. And in other words, this would have been absolutely impossible to cover all 10 of these problems in a half hour. It's just too difficult of material. As you can see, we only covered 4 of them in half an hour. So, all right. Jake, have a good one. I'll talk to you next week.
Yeah, you too.